Welcome online lecture series. Today, in continuation of the previous video lectures, previously we have seen the long distance path loss model. So now, today we have seen the next topic, that is the long distance path loss model. So, long distance path loss model is uh, second approach of your this thing, theoretical and measurement based propagation model. So here we are writing log log distance path loss model. Path loss now both the theoretical and the measurement based propagation model indicate that the average received signal power decreases logarithmically with distance. So whether in outdoor or indoor radio channels, such model has been used extensively in every theoretical aspect. So here the average large scale path loss for an arbitrary transmitter receiver separation is expressed as a function of distance by using a path loss component n. So that's why in this previously video we have written that path loss distance d is directly proportional to the distance upon d upon actual distance to the reference distance component of n, and we are taking the log for the path loss PL, and that is equal to PL dB is equal to tan log of transmit power to the received power, and that comes to minus tan log of lambda square upon 4 pi का whole square into d का square, and we are seeing that there is a n is the path loss exponent, in these equations, and we have seen indicate that the rate at which the path loss increases with distance, it is increases when the path loss d naught is like reference distance is increases. So with the reference d naught, so we what we do now, okay, d naught is the closest in reference distance with the determined from the measurement close to the transmitter, and d is the separation distance between the your transmitter or receiver. So this are two equations are these equations are base equation in the long distance path loss model, and which is in symbol average of the possible path loss values for the given values of the separation distance d. When we plot on the log scale and model this path loss, which is coming in this form. So our graph is coming in a straight line, or after the simulations of this selections of free space reference distance that is appropriate for the propagation environment in a large coverage cellular system, 1 kilometer reference distance are commonly used, whereas the in a microcellular system, much smaller distance such as 100 meter and 1 meter are used. The reference distance should always be for the field of the antenna. So the near field effect do not alter the reference path loss. So our reference path loss is located using the free space pathless model. By using the in a free space, we are writing the PL in dV is equal to tan log of PT to P naught, and that is equal to minus tan log of G of T, G of R, and lambda square divided by 4 pi square and d square. This is a free space and do not any reference distance is chosen in such a way the closest to the transmitter. For a distance when we are using is equal to about 1 kilometer. This is used for the large coverage cellular system. Okay. Yes. So this is a this is the uh, okay. Yeah. So this was the our questions. Now see the next topic, log 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 normal shadowing, log normal log normal shadowing. So shadowing. Yeah, this is the next topic. So model of equations of your first equation you have taken and taking the log of these equations. So it shows the power loss at a distance d b is equal to taking the log on both sides. Come power loss is PLDV plus tan of n log of d upon D naught. ये हमने लिया है, this is taken PL distance D is proportional to the actual distance to the reference distance की power of n, यानी कि path loss exponent. This is D, are taking the log for this side and that side, and it equals to put the some constant. So it is this equations which is written here. It is the model of equations for the path loss. Here, consider the fact that the surrounding environment consider the fact that the surrounding environment surrounding surrounding environment cultures environmental cultures may be vastly vastly different at at two at two at two different location having the having the same having the same separation distance dr, the transmitter and so this leads to measure the signals which are vastly different than the average value predicted in the our equations, and the measured value, why, because क्योंकि ये चीज हम बार बार कह रहे हैं कि जो टावर लाइन ऑफ साइट पे है इसकी डिस्टेंस और जो सिग्नल्स रिफ्लेक्ट होके या लाइन ऑफ रिफ्लेक्शन की वजह से रिफ्लेक्टेड होके या स्कैटर्ड आ रहे हैं, इन दोनों के बीच में जो भी रेस आ रही हैं इनकी डिस्टेंसेस इक्वल नहीं है. दिस डिस्टेंस और दिस डिस्टेंस इज नॉट सेम, क्योंकि ये ज्यादा वेव डिस्टेंस कवर कर रही हैं. तो ऐसे में जो मेजर्ड वैल्यू है that is this by the surrounding environmental cultures, that values are different, and जो expected जो calculated value and measured value both are not same. So that's why it is only depend on any values of d. So what we are this lead the this leads to measured signal which are vastly measurement have shown that shown that at any distance of d, distance of at any so so the path loss, that is PL bar, PL at distance d at a particular location location at particular locations is random because signal is also in random to reach at your receiver ends. So location of your connecting by the transmitted signals is also in random and distributed distributed log normally, or you can say normal in dB. In dB. About the at about the your mean distance, about the So the mean distance value, and that is PL distance of T in dV is equal to power in dV in dV equal to power loss at distance T plus some constant sigma, and this sigma is suffix of x sigma. So you can see PL of, put this equations value tan of n log d upon d naught plus x. So the x sigma, sigma is a mean Gaussian distributed random variable in dV. It is the standard deviation. So ये है standard so now see PL at distance d in dV decibel is the power loss distance, line of sight and reflected signal, plus specific surrounding environment filters that signals is also received by the receiver. That is this zero mean Gaussian distributed random variable sigma n, and here we are putting the PL distance values that is the P power of loss as closest distance, that is the reference distance, plus power loss में जो 10 and power loss coefficient into log of actual distance to the reference distance, and summation of and sum of zero mean Gaussian distribution random variable x sigma. So this is the important in log normal shadowing, and you know the power at distance d is computed dVm क्योंकि because of random energy antenna gains and also power loss distance as d, that is the transmit power in dVm, and path loss during the traveling the distance from the separation distance d so it is the important equations. This is the also important equations, and antenna gain are included in this power loss distance d. Antenna gain is power loss at distance d, where x sigma is a zero mean zero mean Gaussian distributed distributed random variable in dV with standard deviation with standard deviation sigma, that is also in dV. So the log normal distribution, the log normal distribution describe the random shadowing okay. Okay, so shadowing effect which occur over a large number of measurement measurement location location which have the same t minus the separation distance transmitter or receiver separation. But have the different levels of culture different but have the different level of culture on a particular on the propagation path. Propagation path. So this phenomena is referred to as a log normal shadowing. So this is a this is a refer refer as a refer as a log normal So log normal shadowing implies that the measured signal level at the specific TR separation has the Gaussian in normal distribution and about the distance dependent mean of the equations. So when the measured signals level have values in dB units, the standard deviation of Gaussian distribution that describe the shadowing also have a unit in dB. Due to random effect of the shadowings are counted for using the Gaussian distribution, which leads itself readily to evaluations. The close in reference distance denote the path loss exponent n, and the standard deviation are statically described the path loss model for arbitrary locations having the specific transmission and separations, and this models and in this models it may be used in the computer simulations to provide the received power leads for the random locations. So so received power level for the random location in communication system are design and analysis. In practice, in practice, in practice, the value of the value of path loss exponent and standard deviations are computed from the measured data. Are computed from the from measured data. Using linear regression and such, the difference between the measured and estimated path loss model is minimized. So measured value and estimated values are minimized a mean square error sense over a wide range of wide range of measured location and separation distance between transmitter or receiver. So the value of so the value of PL P do not in the equation L path loss at distance d in dV is equal to path loss distance do not plus tan n log d actual distance to the reference distance plus x sigma. X sigma is based on either close in measurement, either close in measurement or on a free space. Assumption. Assumptions from the transmitter to to do not. So how we calculate the path loss exponent? There is a one diagram which is in a graph form. This is plotted between the separation distance TR, transmitter to receiver in kilometers, and the path loss is taken y-axis in dV, and exponent of path loss component exponent are taking in the just opposite to the y-axis. So this is the TR separation in kilometer, and here path loss in dV. And at this point it is 0.1, here closest separation distance 1, this is 1, this one is the origin, this 1, 2, 3, 4, 1, 2, 3, 4, and naught is N1 and 2 and 3 and 4 and 5 and 2.7, and then sigma is fell, standard deviation 11.8 dB, and this is divided into 70, 80, 90, 100, 110, 120, 130, 140. So the plot is like a way. It is started from 1 for the when the values is n is 1, and it is coming this point. When n is 2, when n is 3, क्या हुआ? कौन है? मेरा हाँ नहीं हुआ नहीं है। एक मिनट बस ये बस एक मिनट रुकिए।